Hey everyone, and welcome to The Explainer. Today we are diving into what is literally the ultimate cold case. For millennia, humanity has looked up at the night sky and asked one really fundamental question. Exactly how old is the cosmos? Today, we're going to explore the incredible science, a few historical missteps, and the cutting-edge math that scientists use to pinpoint the actual birthday of the universe.
Look, I'm going to give you the answer right up front, so we can get right into the good stuff. 13.8 billion years old. Give or take a super tiny margin of error, this is the staggering number that modern cosmology has confidently arrived at. It's an incredibly precise figure, and it represents a completely unimaginably vast expanse of time. But how exactly do we know that? Right? Obviously, humanity wasn't standing there at the beginning with a stopwatch, so we kind of have to act like cosmic detectives. We have to analyze these faint, super ancient clues left behind in the dark of space, just to piece together a timeline that spans literally the entirety of existence. So to solve this giant puzzle, scientists basically rely on two primary independent methods. Method 1 is all about finding the absolute oldest objects out there, specifically ancient stars, and calculating their age. Method 2? It takes a totally different approach. It's about measuring the universe's current rate of expansion and just mathematically rewinding the tape all the way back to zero.
Okay, let's dive right into clue 1, the oldest stars.
Think of astronomers here as cosmic archaeologists, right? To find the oldest surviving artifacts in space, they go hunting for these things called white dwarfs. See, when a star like our sun dies, it sheds its outer layers and leaves behind this dense, cooling core. Think of it exactly like the glowing embers left over after a campfire goes out, because we actually know the physics of how fast these cosmic embers cool down over billions of years. Just checking their temperature tells us exactly how long they've been burning out.
So pointing the Hubble Space Telescope into deep space, scientists stared into this ancient star cluster known as M4. They managed to measure 600 of the absolute dimmest, coldest white dwarfs in existence. And their math revealed something amazing. These dying stars are about 12.7 billion years old. You add the roughly 1 billion years it took for them to form in the first place, and boom, we get a really firm lower boundary for the universe. It absolutely has to be right around 13.7 to 14 billion years old.
All right, moving on to clue 2, rewinding the cosmic expansion.
Think about it like an accident investigator. If you see a car driving away from you at 60 miles an hour and it's currently 60 miles away, well, you know for sure it left exactly 1 hour ago. We do the exact same thing with the universe using something called the cosmic distance ladder. By using standard geometry for the closer stars and then specific standard candles like Cepheid variables and Type 1a supernovae for things further out, astronomers can measure exactly how fast distant galaxies are speeding away from us. And that gives us the Hubble Constant, the exact rate of cosmic expansion. But honestly, we have an even more ultimate tool to rewind that clock, the oldest light in existence. It's called the cosmic microwave background, or CMB. Roughly 380,000 years after the Big Bang, the universe finally cooled down enough for atoms to form, and that released this brilliant, blinding flash of radiation. Today, all that light has stretched out into microwaves, and it just lingers there as this faint, glowing footprint of the universe's actual birth.
By running the data captured by ESA's Planck Spacecraft and the Atacama Cosmology Telescope through massive supercomputers, scientists mapped out these super tiny energy fluctuations in that ancient light. This CMB data is basically a snapshot of the early universe, telling us exactly how fast it expanded right at the beginning. It completely locks in our age at 13.8 billion years with a staggering margin of error of just 1%. That is an absolute triumph of modern science.
Which brings us to a really fascinating chapter. The historical age crisis.
So, puzzle solved. We can all pack up and go home, right? Well, not exactly. Relying on these expansion measurements actually caused a massive head-scratching paradox back in the day. Back in the 1920s, Edwin Hubble's initial math suggested the universe was only about 1.8 billion years old. But then, by 1955, geologists dated the Earth to 4.55 billion years. So, yeah, the universe literally appeared to be younger than our own planet. No way, right? It wasn't actually until the 1990s, when scientists discovered dark energy and realized the universe's expansion was actually accelerating, that the standard model finally fixed the math.
But of course, the plot thickens. Let's talk about the modern Hubble tension.
Because science is never truly finished. Today, a brand new crisis has popped up, and it has cosmologists completely divided.
Look at this. When we measure the local, nearby universe using our standard candles, we get a Hubble constant of about 73 to 76. But when we measure the early universe using that ancient CMB light we just talked about, we get a noticeably slower rate of around 67 to 68. The two absolute best measuring tools in all of astrophysics fundamentally disagree with each other. This is the famous Hubble tension, and it strongly points to a massive blind spot in our current understanding of physics.
So, how do we solve this? Enter the next cosmic chronometers.
To break this crazy tie, we really need a completely independent way to measure expansion. And that's where this incredibly cutting-edge method comes in. Now, I know the underlying math here looks super complex, but the core concept is just beautifully elegant. Instead of trying to measure the absolute age of the entire universe from scratch, this method brilliantly simplifies things. It just measures the differential age of galaxies. Basically, they find old passive galaxies whose clocks started ticking at the exact same time, and they just measure how much those galaxies have aged between point A and point B.
This is a total game changer because it completely bypasses the massive headaches of calculating absolute ages. By analyzing specific features in the light, like this thing called the D4000 break, scientists can basically create a pure standard chronometer. And here is the absolutely crucial part. Unlike the CMB measurements, this gives us a direct expansion rate without forcing us to assume any specific underlying model of the universe. It is the ultimate unbiased tiebreaker.
Which brings us to a final kind of thought-provoking quote to leave you with. Today, thanks to ancient cooling white dwarfs, the microwave afterglow, the Big Bang, and the complex math of cosmic expansion, we confidently stamp the universe at 13.8 billion years old. But, as our sources remind us, science is always evolving. As we deploy these brand new cosmic chronometers, you have to wonder, could the Hubble tension be hinting that our current certainty is about to be turned completely upside down? Is the universe actually older, or maybe younger than we think? Honestly, only time and a lot more data will tell. Thanks so much for joining me on this explainer, and I'll see you next time.